how you get it. You need the indicator. Right? And then you do it with 200. There we equal 200. And then we have the other one. Right? So there are now 3 columns in this. So 250 and so on and so forth. So these are the averages. Okay? And maybe let's just sort of start with the following. So I'm basically generating this red, some column which I call it signal, alright, which is 0 first. So there's nothing in there. No basic quantities in there. That's a new column which I call it signal. And that's the signal based on which I will act. I will do something, buy or sell. Alright. So here then I go in red, and then I use the log. Alright. And look at the red, SM A50. SMA 50. Alright. If it is above red, SMA 200, alright, then signal should take a value. Alright. Wait, let's say 1, so signal 1 means buy. Alright. So 1 is buying. And -1 is selling. Alright. And 0 is nothing. Just wait. Don't do anything. Okay? Just wait. So that the signal switches, so one becomes 1 or -1 and then so should this now be 1 or minus? Okay. Look, this is the short mean. Right? It's above the high mean. Right? Let's look at those. So this is the short mean. Above the, so some of the first time that it happens. Say, that's actually not a very good one. So let's say we have the time like so. Let me just make the graph a little bit more. You said -1. You think it should be -1? Yeah. And so this is the one. Right? So say here. And that is the red. Right? So they are next to each other. So the red has a higher mean. This is here. And the black is a slightly lower. So here we are on the rise. The things are seen. So it seems like we are increasing. What should we do? Fine. We are on the rise. Wait a moment, so I'm doing it with the returns. Wait a moment. This shouldn't be with the returns, but rather it should be with the prices. So let's call it data. Sorry, that was just off. So we're not looking at the returns, but rather at the prices. Alright, so now what is your answer? Okay, sorry. It was not with the returns, it was with the prices. So prices just start to go up, right, compared to their longer term. So this is not the returns, the prices. So prices are on the rise, you should find them. Right, so that should be 1, not minus. So maybe that was what I misled. So that is the data. prices are going down. Right, so better sell because they are going down. So I will lose if I keep. Is it clear? So look, I mean, the point of this is to understand that the prices are, when we hear sort of more or less understand that we are getting up. Alright? Maybe we understand a bit earlier. Yes.
Oh, I see. So, can you do something? We have to define interbank higher in the long run. So we can,
If the red dot is above the black,
yeah.
then we buy. Right? Why? Because we have a rise. So that we will understand this a bit earlier. So maybe earlier we will understand. Not here, but rather maybe there. So that is sort of this is the longer one, and this is the short. The shorter is here, right? So it will give us a mean which is there. But this other one, when we understand, we generally understand earlier. That was somehow was too much in the rise. So the first time that sort of the short time becomes the short basically average becomes higher than the longer one, then it means that we sort of are on the rise. Potentially maybe increase. And then we buy here because we want to sort of benefit from it. Afterwards, the prices may go down. So when they are going on the sort of downwards, the order will switch. These two dots will switch the order. And that means that we have to sell because the prices are on the downward trend. Yeah.
Do you want to this on the red and the black overlay channel maybe just have a little bit gap.
Yes, that's true. So maybe they are too close to each other. So it will be sometime that one goes up, one comes down. Maybe let's look at them. Right? Let's look at the averages, the prices, and also the long average, the short average. Let's take a look. Maybe that will be a little better. Alright. So let's say we do the plot of the prices, which are data and assets. Alright, so here we have the label. The label are the prices. Alright. Now we do so that is the 50. Alright, so here we go in data SMA 50. Alright. And then we have a 200. And PLT will show. We need a grid and blah blah blah. So let's say we have the legend and let's do it. Let's now look at those. And then see how they look. Oh, there are not so much C because there is a lot of series. Let's maybe take the prices off. Alright, so that will be a bit better to see. Okay, so the 50 is the blue. Alright. So the 50 is the blue. And the orange is the longer one. Alright. So for some time period, so sort of here, then we have orange below the blue. Alright, so here, let's look at this. Right? So the blue went above the orange. Okay. So let's now look at the prices too, together with them. So these the prices are now blue. Alright.
The prices are blue.
Here are blue, yes.
Yeah.
And then say 50 is above the green. Alright.
Yeah.
So here is the place where we buy. And we don't do anything. Just keep till they swap. And that is there. it is very easy. And we do just close our laptop, buy it, go home. But then we always keep checking this. When the day that they swap each other, then we start selling. We sell. And that's it. Then we wait till the signal becomes 1 again. And that is when the orange, well, when they swap some. Alright, so they seem not to look like, so maybe there is sometime a bit later, so that's 2023, where the orange goes up. That's again this time period where there is a rise. And then we buy again, and they swap, then we sell. And we go on and on. So there is a period where we don't do anything. Alright? There's a period where we buy, and there's a period, so the time period where we sell. Okay? Well, depending on these two averages. Okay? But now the thing is that this is sort of in actual data. So we have to indeed look backwards. Right? So we have to look at the data yesterday and then say something about the future. You know? So we need to make a decision based on the past value about tomorrow. And then you sort of, but these are the signals, so plus and minus and so on and so forth. Right? So, but if we could use this strategy, so to calculate the need and get, say, some prices, right? Then we can go on and then calculate how much we earn. So that will be the difference between the point that we have here and then the point that we so this is where we buy at 50, and then we sell at when the Apple price in 2022 was around 151 or so. All right. So, well, 100 euro. So the price is 50. All right. So that's the price index. So we buy it at 50 and sell it at 150. So we would have earned 100. So that's not so much, right? But still, when I mean, compared to this index that Juan has bought, then this is actually, well, it also brings something, but over a longer period of time. Right? So we're not 3 months, rather long. Okay? But in any case, so we have a C. So there is a minus and a plus. Right, but of course we have to do, say, back testing and so on and so forth. So, which is not a problem. Hello. This phone. Good to see you. So we just make a small break. We have to do some stuff. So here. Here. This is green. That's it. Eight. So we can basically say, so here we have the data, let's call it the returns of this basically asset. Let's calculate the percentage changes. Okay, so the returns of AAPL. So that will be just for once you do that. So that will be data at asset, and then PCT change. So that will be just the percentage changes. Well, always we did loss, right? So that's the first time we do the percentage. And then for PCT change, every percentage change, then there is this little method which calculates the percentage changes for us. That's a pandas story, which is nice. And then let's calculate the strategy returns. So if we do this, then how much do we return? So the strategy returns. Let's put it that way. And that will be the data and returns. What returns? Data returns of Apple. Well, times the data signal. This is about what we do, so we buy or we sell. Alright? Because once we sell them, we go short. Right? We can basically do it that way. If we shift it by one, we look at yesterday. Right? So we can go long and we can go short. When we go long way, so that is what we have, right? So that is like the signal. But then we can calculate the cumulative returns. So the cumulative returns will be well, 1 plus data strategy returns become product. So that will be product. Cumulative product, right? So that will score the product or product. This is the change, strategy, product. There is product. Yeah. So we get basically cumulative, basically moves. Right? For all of this, basically strategy, plus minus, long short. And you can plot it, look at it, so analyze it, and so on and so on. Maybe the easiest one is that you look at the signal, is it plus or minus, is it minus or seven? And then rate till, if you don't want to go short, right? Put minus. And then we can do other strategies. Back here.
Yeah. Are you happy with this simple method?
So it picks, essentially, it picks the trends. I mean, momentums are also interesting. Those that are based on the volume, also, I don't have the volume data. If I had, then I could actually talk about the volume. It's called product. I also have the product. And I did it on product, but then it is called product. Not the use. You can plot this. But the point is that you get the trend. This is called the golden cross. This strategy. So my basing is golden cross, then you make this. Okay. So I build this and then I give you this technical analysis library. You can take a look and see so on and so forth. There are many. And then there is always this, what I like about that is that it has this nice link. Alright, so how it compares to the MAC. Let me read. Right. I think that's enough. So let me go back to the slides, the last slide. Alright. That I wanted just to talk a little bit about forecasting. But that's actually a very, well, oftentimes involved, complicated sort of task to forecast returns. But the return should be somehow, there should be something that is helping us predict them, right? Something should exist that we could use to predict essentially the returns tomorrow. Right? Oftentimes from theory, one says, well, okay, so if it's about forecasting, then it doesn't matter what predictors you bring, whatever you can think of, make the p-values, macroeconomics, cycles, and so on and so forth, right? But I mean, theoretically, or sort of maybe rationally, it makes sense that if I have a returns, right, then they should be related to financial ratios. Financial ratios actually tell us something about the well-being of the firm. So they should include some information with respect to its rise or fall. Alright? Okay. Well, that is sort of what it should be. Okay. Well, let me talk a little bit about that. Then let me just move those. Just to tell you how hard this could be. I mean, that's sort of more of a graduate PhD type task. It comes to the theory, but I will tell you, because it's very simple. Methods may be a little more interesting. Well, let's say we have some variable y, and then we want to predict it with some predictor. That's sort of what we have. These are two financials here. This could be some excess return. That could be a financial ratio. So xt minus 1 could be a financial ratio. But because it's a financial ratio of the same firm, then well, let's say look to market value. This period depends on what it has been last year. So it's a dynamics here. So the speed is xt, well, it has a mean and depends on the past. Right? Well, I mean, essentially what we have is that we have a predictor, and the predictor is persistent. Right? So that's sort of what we want. And then, so the question is essentially whether beta is 0 or beta is non-zero. If it is 0, then there is no predictability. If it is non-zero, then there is predictability. And so this guy helps predict that. Because that's t minus 1 yesterday, and that's today. Right? Now, oftentimes this becomes a little bit complicated. And why? Because this rho oftentimes is very close to 1. Too close to 1, so it becomes 0.99. 0.99. So then people thought, okay, let's make this a little bit more appropriate for the analysis. And they basically assume that this rho is a function of t, sample size. When the sample size grows and becomes larger and larger, right, then this rho actually also adapts itself. And specifically, one writes it like 1 minus c divided by t. T is the sample size. Right? And c, say, some positive number. Okay? Well, let's say sample is 1,000. Alright, then you have 1 minus c divided by t would be
be a very small number c divided by t. 1 minus that will be a number very close to 1.
So this is indeed something which we call it local to unity specification. Local to unity specification. So let's look at the unit specification for the persistence measure of the turbine. Okay. So, well, if it is actually 0.99, then this xt will have a very big variance. It's very close to a unit, so that's a very large variability that you have in xt. Right? On the other hand, these are returns, and they don't vary much. Right? So something that doesn't vary much, you want to predict it with something that varies a lot. Right? So that becomes a very hard regression. Okay? Unless you take into account the fact that this row is very close to 1. If it is, then it may become more isolated like that. That's part of the model. And then you can go on and then make the model more adapted to the actual characteristics or properties of the data. But there is also another problem. The other problem is that that's the financial ratio, which has this specification with this error. And that's the return with this error. Right? So these two are generated in the same financial system. Right? So generally these two are dependent. Because there are shocks in the same financial system, they're purged with the same stochastic components, so they may be dependent. They are independent. And then well, this epsilon t may not be IID, it may actually be an MA process, MA10, or maybe it should be an AR. Right? So this depends on the past values of this shock. And as such, then these two, because they are correlated, then this and that will be correlated too, as long as epsilon t depends on the past values. Right? So not only do we have rho very close to 1, but we also have endogeneity. Right? So then the calculus becomes very hard. So we have an endogeneity problem. Oftentimes in this basically frameworks, you can estimate beta properly, you can test for this properly, and then things become very hard. Then if you add another dimension to the complexity that is here, is that, well, we just now saw for the returns of Apple that there are at times weak data effects. And that means that the means actually change. Sometimes they are 0, sometimes they are +1. So smoothly may change. Right? So then oftentimes this is actually time varying intercept. So that becomes even harder. Right? So you have to deal with it. Right? So deal with all of this. Okay? This is something which I will not now go too much through. Right? But that is something which is called the predictive regressions. That's a predictive regression. It helps us predict something about the future. Alright? So alpha may be constant, maybe not. Well, I've seen evidence we just saw a few hours ago. This may also be time varying. This is close to unity. We are independent. So then testing about predictability becomes complicated. Right? I've worked on this for some time. Right? We post one of my actual working papers on this topic for you to read. Right? So the reading list becomes longer and longer, but that is just for the fun of it. Also so that you know what I do. Right? So it brings us a bit closer. Maybe later you have interest in this and we can work together. If you do it each. So, but in any case, the predictive regression is that depending on the type of the variable x that you bring in, then you may take, so you may say, so this x is close to unity, I have an homogeneity, but dynamic, this may be time varying, but how to estimate that? Or how to test for whether predictability exists or not. Right? So that's quite fun. And for the paper that I have, I post online, so that's a theoretical paper. So sort of
puts together the methods that you require to do the testing and the estimation, but also has a small few pages of application. Alright. So there are some literature that I look at, and that could be just interesting. Maybe it's interesting, maybe it interests you. And then you look at sort of what variables one can use here, at least. Right? And so on and so forth. So that's sort of what I wanted just to talk about this very briefly and link you to. And I'm essentially done with this section 2. We have one more section, which is on factor models. So there will be a little bit of linear algebra, but also a bit of Python programming. So that will be a bit theory, and then we will do some programming. Let's start the theory today, till 12, and then tomorrow I will finish, and then whatever hours if you have left, then I will start doing the exercises that I post on that. Okay. But it will be great if you take a look. I will update the assignments tonight. So we'll add another one. With Markov processes and so on and so forth. That will be more fun. Good. So let's just start with this section. Do you have questions before I go? This is not part 3, so I have to fix this, but somehow part N, part last. But let's see, so this is about factor analysis, or factor models, right? Well, I mean, factor analysis tries to find few driving forces that you have behind the data. So, we know what is inflation, right? How do we calculate inflation? It's a very simple question, but I want that you formulate it in words. But you need the price index for it. And then the changes in the price index becomes the inflation. Right?
Yeah.
The prices go up. On the price index, so that's the question, how do you calculate the price index? Then you look at how much is the paper. Right? So how much does this cost? How much this exists somewhere? And then you buy it as a price. You have books, you have, say, service sector, you have construction, so on and so forth, right? And then you take them to form a basket of goods, and then calculate the prices, that becomes the price index, which you may know, essentially 200, say, 2,000 yen.
So the price index is the average price.
That's true, that's a weighted sum. It's not an average, it's a weighted sum. Remember, every second we get a bigger rate. So the industry may get a lower or higher rate. So sort of there are different products, so they come together, and then you get a price index. So that's a weighted sum. And then there is something which is accepted or formalized, central banks use it, and then they generate some price index. That we can basically use it for understanding the inflation. But if you change the weights, if you change the basket of goods, then you come up with some other index. Right? So, well, indeed, what you do is that you bring in some factor, something which is representative of all of the variations that come in your code. This is what factor models are. And you have many series, and factor model shrinks them to 1, or maybe 2 or 3. Right? So one factor that we know, and it's interesting, is inflation. Because so GDP is also, right? That's what. So you have some different business components from the Bachelor of Economics course, macro, and you know how to calculate GDP. Right? So there are simple components, and you add them together, and you say this is the gross domestic product. All right? So that's sort of what we know, how it is calculated. That's also a combination of certain things that come together. Factor models are also like that. So the idea is that why do we actually calculate the price index? Because there are so many products. How do you want to talk about it? It doesn't really work. And as such, then you work out some conventionally accepted way of combining all of those prices with certain dates, and then you stay with it. You say, this is the price. Right? This is not the true price. But these are not the true prices, but they are an index thereof. Right? So that's something that includes some variation, some changes in the prices with those dates. Right? Fractal models are actually made for this. Right? So from statistics, then so you have say many series. Right? Could be many units, so sort of a pen, a table, a shoe, and so on and so forth. But if you add them together, units could be countries. For example, what is the inflation rate in euro area? Alright, so there is a euro area inflation. There is a German inflation, there is a Greece, but there is also euro area. Right, so that sort of is perched on the local prices somehow, and there is a formula that does the calculation. Right? And the thing is that so the fractal models actually help us shrink the information in one variable which is easy to understand and analyze. Yet it includes a lot of information about the underlying components. Right? So that's sort of what we have. So one of the statistical, for calculation of the price index, then you have some agreed upon weights. Yeah, that are agreed upon. But then if you don't have that, all right, for say if I have many data and I want to shrink them, make them smaller, make some index out of them, then I turn to a statistical tool which is called principal components. All right, so principal component analysis. You have heard it before, right? Yeah, so you knew these stories that were. Yeah, so I will do that again, so that will be a reminder. It's always good. But let's see how does that actually work. All right, this you also know. You haven't done derivations of principal components. Maybe you have, maybe not. So I will do them. I will rewrite this. But let's say you have a k-dimensional vector of random variables. There are k can be 100, 20, 50, whatever. Right? And then without loss of generality, let's say that there are 0 mean. And mean of this basically vector is 0. Okay? And then they have, because they are random variables, then they have a covariance matrix sigma. Right? So the sigma summarizes all of the variations or variability, variance, that is what the name is, of the data. Right? So second moment, variation around the mean, which is 0, then becomes a variance. So variation will be sigma. Right? Now remember that I put that we are after a Alright. So when we were actually with the inflation, alright. Then what are we doing? We basically for the price index, then we have different series and forming a linear combination of them. Right? So that is what we also do. Right? So let's say I have this x, and then I form a linear combination. That becomes an index for some a. I'm not saying what this a is. You have to choose this a wisely. Right? So let's look at the variance of this. Right? So that's a vector. This is a vector. So the variance will simply become variance of the. These are matrices. Right? So that will be variance of. So that is a prime exactly. Then comes the variance of x and a. Right? So this linear combination has this variance. Right? If it was univariate, then a would have come to the power of 2. Right? But because they are vectors, then we will have a prime a. That's also to the power of 2 as we have, as you know. Right? So that's not neat. Okay. So far so good. But the variance of x we started with, so that is a prime sigma a. That's a quadratic form. It's a quadratic equation in a. Alright. So now we want to basically find these a's somehow. Alright. In in such a way that this variance is maximized. We want to maximize this as big as possible. Alright? But well, I mean, of course, we choose A to be close to infinity, and then to be as big as possible. But we normalize these A's. We make them to have a unique length. That's the, yeah? So you understand, this is a norm. So there's two lines. So here we're going to basically be maximizing. We're going to go after maximizing A prime sigma A, subject to, well, these A's, square root of A prime A to be 1. Now that's the length of the vector. The length of the vector is, for example, let's say you have a triangle like that, and this is 3, this is 4, then the length here is 5. So 3 to the power of 2 plus 4 to the power of 2 square root. This is what we do. Alright? So these A's we choose in such a way that they have a unique length. So for example, let's say this is A1, and this is A2, and the length here will be the square root of A1 squared, A2 squared. Alright? And then we choose this A and A1 and A2 in such a way that this is so that's one of the restrictions that we have. And then then we can solve this. So that is not actually hard to solve. Right? Can you solve it?
Lagrange.
Yes, please. Do the Lagrange. That's an equality, right? Constraint. Well, I mean, if the length is 1, right, then you can also look at, let me simplify your life. So if you take the power of 2, because if the square root of a number is 1, then you could do the power of 2 also. Right? So that's the Lagrange, right? Now we need the first order conditions. So these are matrices, right? So we need a bit of matrix calculus. Right? that's a vector, then we take the derivative with respect to a vector, then it's, we can do it element wise, with the first element of A, then the second element of A, and so on and so forth. And then we give a vector, and a column vector. So that's very important to keep in mind. So here the derivative will be sigma times A, so that you get a column vector. Correct? Not one times, but let's sort of do it, so that will be two times, one times. First comes the, what is like a bread, right? Like a sandwich, like a banh mi. So that's the bread, and this is the one that you have in the middle. This middle one shows up in the beginning. Right? So first you see the bread, and sorry, the butter or whatever is in the middle, then comes the one part of the bun. So let's take a derivative of n with respect to a, then it becomes, well, the 2 remains. So the 2 sigma a. And that's also the same, and the sigma is 1. Right? So here, well, sigma, there is nothing. Right? So it's just nothing. It's just a free, just a bar, nothing in the middle. Right? So then here we have minus 2 lambda a. Right? And then we set this equal to 0, of course. Right? I mean, let's say the value that solves this, let's say this is a1 equals lambda a1. Right? That's an eigenvector. Because we pre-multiply, we post-multiply this is a matrix with a vector, then you get the same vector back in the direction, just the same vector, with a scale. But that's something that we call an eigenvector. You know, the German word eigen. It's own. It's its own vector. And this is the eigenvalue, which tells us essentially something about the contraction or the expansion of the vector after this transformation. Right? So that's an eigenvector equation. So if I want A1 and lambda, I have to solve for the eigenvector and the eigenfunction. Sorry, not eigenvalue. Right? So we can solve this equation. Alright? That's not a big deal. We can do it with Python, we can do it by hand once we have the sigma. Right? But now the point here is that A1, which is supposed to maximize this, is the eigenvector of sigma. Right? So that is the principal component. One of the principal components that we have is the eigenvector of the covariance matrix. That's a vector. So that's a basis. So if I choose this, A1 has the eigenvector of sigma in such a way that it is normalized to 1. That's on the unit sphere, where that's a sphere of radius 1. Right? Then this will be maximized. So we will get a linear combination of x in such a way that we capture as much variability as possible. That's the idea of the principal component, which we call it one of the factors, essentially. One of the factors that you have is this linear combination. Right? So if the sigma is, say, 2 by 2, then how many eigenvectors we have? 2. So there is 2 different ways that you can put these two together, the components together, and have as much variance as possible. Let's maybe continue a little bit with this. Yeah. Alright. And then afterwards we do a numerical. That is what we have. So Well, let's plug in, well, that's, we know what is A1. A1 is the eigen vector. Maybe let's call this, because I called it A1, then this will be also lambda 1. So that will be the eigenvalue with respect to this function. So let's look at the objective function, which is A prime sigma A. And we evaluated at this eigen vector. Alright? And it will be what? It will be A1 prime sigma A1. Alright? So let's just plug instead of A, so free variable, the eigenvector that we have. But sigma A1 is lambda A1. Right? So this is equal to A1 prime lambda 1 A1. Right? So simply instead of sigma A1, we're plugging the value from the first order condition in problem. What is A1 times A1? Yes. So then this is what? Lambda. So this lambda 1 is the maximum value of the variance that we get. Right? So that is the maximum. That's the objective function. The value of the objective function at this optimum is lambda 1. Right? So that's the maximum value of the variance that we get. Right? Well, so that's sort of one of the eigenvalues, right? But we can actually look at other eigenvectors and eigenvalues too. Right? But so to speak, if this is, well, that is the first principal component. Right? And then, so I mean, there are many lambdas. For example, let's say if my matrix is 2 by 2, then there are 2 eigenvalues. And obviously, I wish this to be the bigger eigenvalue. Right? So that the maximum is as big as possible. Right? And the other one will actually capture a smaller variance that we get. Right? So one lambda may be higher, the other may be lower. Let's calculate sort of redo this. So for the other eigenvalue. Alright? So here I will maximize, but let's say we maximize it, I will specifically just give an index 2 to this. Alright? So A2. Alright, so A2 should be normalized. But what I want to have is that A1, which I have derived already here, right, should be orthogonal to A2. So that there is no covariance. If they are orthogonal to each other, and then one will be like so, the other will be like that, and they will not be actually variant with each other. There will be no covariation. Right? So A1 I found, and then I will now go find the other factor in such a way that it is orthogonal to the first. Right? So now the Lagrangian will be a little bit different. Remember, so let me just write the first order condition that we had was that in the previous one was that sigma A1 is equal to lambda A1. So let me keep in mind. Now I want to find another vector that we have, another combination, in such a way that it is also of length 1 and it's orthogonal to the other. And we can write the Lagrangian. So here I will have well, the Lagrangian will be what? Will be the objective function A2 prime sigma A2 minus, so let's put this lambda 2 A2 prime A2 minus 1. Then minus, say, some other lambda or some other parameter. Let's call it theta times A1 prime A2. Now we go on and then write down the first order conditions for this guy too. Right? So that's sort of the other basically quantity, right? So if I take the derivative, then here I will have sigma A2, okay, minus twice lambda 2 A2, and then here, where when I'm taking with respect to A2, then I get right, A1 equals 0. Right, now we have to solve this equation, right? We have to solve this equation. Okay. And we know something, right? So we know that A2 prime times A2 is 1, A1 prime times A2 is 0. Right? So these are what we know. So if I sort of here, well, I mean, if I bring or both multiply with A2, then this term will drop. Right? That's sort of what I know. That will drop. So do it at home and then show that sigma A2 becomes lambda 2 A2. So just play around with it. I just want that you sort of challenge yourself a little bit with solving this. Okay? Alright. When you do that, then you get this. So you get sigma A2 equals lambda 2 A2. Alright? That will be sort of what you should get. But use these two. And this. The first of the condition that we have from the first. So we know that it's an eigenfunction. Alright. Then you will get that right. So the second eigenvalue that we have here is in such a way that it's also normalized to 1, has a length of 1, and it is orthogonal to the first. Alright. Clear? Well, I mean, that you can do too. So if you take the derivative with respect to x and then set it to 0, then you get this condition. Right? So that is what I mean. That you take this condition also into account. If you take a derivative with respect to lambda 2, set it to 0, then you get this condition. So these two should be binding. Exactly. It should be equal to 1. This is our length 1, and these are orthogonal to each other. So they are like so. Right? You take this. And so just leave it for now, and then you try it at home. But now, in the same way, we can go and then do some calibrations of the objective function with A2. Alright. So if I look at the objective function sigma A2 sigma A2, then, well, using the same logic, then I get lambda 2. Alright, so lambda 2 will be the value of the objective function. Well, so to speak, we decompose x into two orthogonal components, a1x, so a1 prime x and a2 prime x, that they are orthogonal to each other, that they have no covariance. Right? So to speak, a1x, a1 prime x is one of the components. Right? Let's call it principal component number 1. And then we have principal component number 2, which is a 2 prime x. So these are the two ones. Well, oftentimes one speaks of this lambda. Alright? And then if you multiply by that, then it becomes a factor. Alright, so it becomes a linear component. That's the first principal component, this is the second principal. Well, the first principal component, then you form a linear combination has this variance, and lambda 2 will be the other variance. Right? And these are in such a way that lambda 1 plus lambda 2 is indeed all of the variation. There's nothing more. Right? So if let's say, if k, if the dimension is 2, right, then lambda 1 is part of the variance, Lambda 2 is another part of the variance. And there's nothing left. These two summations, lambda 1 plus lambda 2, will be the total variation that you have in x. Alright? That will be the total variation in x. So if you have more than k, well, let's say 20, we will have lambda 1, lambda 2 up to lambda 20. And if you add them together, then will be the total variation that you have in the x. Alright? So let's say, now we can go now and do exercise. So now we have some calculation for some matrix, and lambda 1 becomes 0.9. Right? And then let's say lambda 2 becomes some other number, let's say 0.1. Right? Say, maybe we do the calculation. Right? So then, lambda 0.9 divided by 0.9 plus 0.1, which is indeed 90%, or multiplied by 100. This is like lambda 1 divided by lambda 1 plus lambda 2, or this ratio. Times me, which is 0.9 here, right, so 90%. Tells me that the first component explains 90% of the variation in x. Alright. And the second component, the rest, which is 10%. Alright. So eigenvalue, yes, exactly. You know, lambda 1 and lambda 2 are the eigenvalues. So, for example, let's say k is 120. Alright, so you have 120 series, many variables. And you want to capture, say, 90% of the variation. Not all, but 90%. Then you can basically say, alright, so let me look at lambda 1 plus say lambda j, right? Divided by sum of lambda j from 1 to capital K. Right? So these are all positive because covariance is a positive definition, so lambda will all be positive. Right? And let's say I choose lambda j equal to 2, and this ratio becomes, so let's say j is 2, and this ratio becomes 90%. It would mean that the first two components are enough to capture 90% of the variation in the sum. So the rest are not important. And they don't take too much of variation in them. Just few, well, just two factors. Instead of working with 120, then you work with 2. Right? These two main factors actually explain 90% of the variation in the data. Right? So then sort of your life may become easier. Instead of working with 120 series, then you work with 2. Where is 2? 2 is not here. And that will be easier for me to handle because you don't have so many series. And as such, in data science, this is called a shrinkage method because it shrinks the variables. Then one should find, say, alright, so 90%, 95%, and so on and so forth. I have one more minute. I've corrected this clock sometime ago. Yeah. So, for example, let's say one variable of interest in economics or macro in finance too. In macroeconomics is the output gap. Output gap is a variable that is oftentimes hard to estimate. Right? It's a function of many macroeconomic variables. There are 100 plus. Right? And then, well, output gap, there's no specific definition for it because you don't know how much your economy can produce at the max. So the maximum is not known to you, but the maximum you should be able to understand the maximum using the economic variables. Alright? So one generally knows when it comes to output gap, then 2 or 3 factors are enough to capture this output gap. Alright? But instead of working with all of those, then you sort of include in your VAR model few factors. And then you get a factor augmented vector autoregression. Fall bars. Maybe you're right. No? No. Now you're right. So they become factor augmented and become easier to work with. So instead of estimating a VAR which is of dimension 130, Then you have 4 or 5 main macroeconomic variables plus 2 factors. And then captures a lot of other variables that you don't have. Or you have them, but there are too many. So you sort of print them in field, and then go on with your VAR. VAR in just one dimension it's possible to estimate. So tomorrow I will give you exercises with these. You will solve them, and so you see, I mean,